Hi everyone, welcome to TechPrane YouTube channel. In this video, we will learn why real-time analytics matters, explain Spark Structured Streaming fundamentals, show you how to spin up a Docker-based Spark cluster, walk through live coding, and share best practices for performance and monitoring. By the end of this video, you will be able to understand core concepts of Spark Structured Streaming. Deploy a Spark cluster using Docker and Docker Compose. Implement end-to-end real-time data ingestion, processing, and storage. Apply performance tuning and resilience best practices. Visualize and monitor your streaming application in production. Why real-time analytics? Immediate insights let you react to events as they happen, crucial for fraud detection or dynamic pricing. A competitive edge emerges when you can detect anomalies, optimize operations, and personalize experiences instantly. Use cases include fraud detection, predictive maintenance, and live dashboards. First up, Spark is a unified engine. That means whether you are running traditional batch jobs, interactive SQL queries, real-time streaming pipelines, machine learning workflows, or graph computations, Spark handles them all in one platform. Next, Spark's secret sauce, in-memory performance. By keeping data in RAM rather than shuffling it to disk, Spark delivers lightning fast processing, often 10 times to 100 times faster than disk-based engines. And finally, Spark speaks your language. It offers multi-language APIs, Python, Scala, Java, and R, so you can build your analytics or data apps in the language you are most comfortable with. Spark Structured Streaming is built on the Spark SQL engine and offers a unified API for both batch and streaming workloads. It supports micro batches, processing data in small time intervals, and continuous processing for sub-second latency. Core APIs include Spark. It supports micro batches, processing data in small time intervals, and continuous processing for sub-second latency. Core APIs include Spark Read Stream and Spark Write Stream to declare your streaming computations. Key concepts like triggers, watermarking, stateful operations, windowing, and exactly once semantic ensures correctness and resilience. It may be like, why use Docker for Apache Spark? This will make every team members to spin up the exact same environment and also help with isolation. And also helps in isolation. Spark runs in its own container. No more it works on my machine problems. And also it helps with easy scaling, which spin up traditional Worker containers with a single command. Now, let us walk through a production-ready Docker file for deploying Apache Spark in containers. Our Docker file starts from Python 3.11 bushel as the base image, so we can install Python dependencies alongside Spark. We define Spark version 3.4.0 as a build argument, making it easy to upgrade Spark later. We update apt, then install essential tools called Vim, OpenJDK 11 JDK, SSH, so our container can download, run, and manage Spark processes. In one step, we call -fsl the Spark tarball from the Apache archive, extract into opt-spark via stripe component, and then delete the archive to keep the image slim. We update apt, then install essential tools called Vim, OpenJDK 11 JDK, SSH, so our container can download, run, and manage Spark processes. In one step, we call -fsl the Spark tarball from the Apache archive, extract into opt-spark via stripe component, and then delete the archive to keep the image slim. Next, we copy in requirements.txt and pipe install, letting us include any Python libs needed for PySpark or your application. We set Spark home and add its bin and sbin directories to paths, so all Spark commands are available. Copy your Spark default config file from the config directory into the image to pre-configure things like master URL, memory settings, and shuffle options before runtime. We set Spark home and add its bin and sbin directories to paths so all Spark commands are available. Copy your Spark default config file from the configuration directory into the image pre-configure things like master URL, memory settings, and shuffle options before runtime. When you copy entry point, you are copying your local entry point script into the container's working directory, which in this Docker file is set to Spark home. Next, run chmod with the entry point. This changes the file mode to add the executable bit, ensuring the shell can run it at container start. Without this, Docker will throw a permission deny or no such file or directory error when trying to execute it. Finally, entry point tells Docker to launch your script as the primary process inside the container. Whatever you pass to Docker run or in your compose command becomes the script's first argument. Here, it is used to select the master, worker, or history workload. Our entry point handles three rows via the first argument, master, worker, and history server. Depending on Spark workload, we launch the appropriate Spark script, ensuring each container knows exactly what to run. We start with usr bin env bash to ensure portability across environments. Then sets -euo pipe fail makes our script robust. Exit on any command fail. U treats unset variables as errors. O pipe fail catches failures in any part of a pipeline. We grab the first argument into Spark workload. If none is provided, it defaults to empty. We echo it so logs clearly shows which row the container is running. If Spark workload equals master, we execute the built-in start master, passing the port from the Spark master port environment variable or defaulting to 7077. For a worker, we call start worker, pointing to Spark master host master port. We pull Spark master host and Spark master port from the environment with sensible default. If the row is history, we launch the Spark history server via start history server, letting you visualize completed job metrics. And finally, we guide against invalid usage. If no known row is passed, we print the correct usage and exit with an error. We create a Spark configuration file with 4 key Spark configuration settings that enable and manage event login and the history server. First, Spark master tells Spark where the cluster's master node lives. Here, we point to Spark master on port 7077, so all drivers and workers know where to register and fetch their work. Next, Spark events log enabled flips on the events logger. With this set to true, Spark will record every job, stage, and task event to persistent storage, essential for debugging and post-mortem analysis. The Spark events log directory setting specifics where those logs live. Using file up Spark events writes logs to the local file system under up Spark events. In production, you might point to HDFS or S3 instead. In production, you might point to HDFS or S3 instead. Finally, Spark history file system log directory tells the Spark history server where to read those same event logs. By pointing it to file up Spark event, the history UI can replay past jobs, letting you visualize timelines, stages, and metrics long after the job finishes. We created a book data directory and created a file called feeder.py. Our feeder writes one JSON file every half second into OptSpark data IoT stream. We simulate 3 devices, sensor 1, sensor 2, and sensor 3. Each iteration picks a random device, generates a timestamp, random temperature, and humidity, writes it to a uniquely named JSON file, and sleeps for 0.5 seconds. Always hit Ctrl+C to stop the feeder. We created a streaming jobs.py file. In this file, we start by creating a Spark session named the IoT streaming demo. To read JSON properly, we define a struct type schema matching our feeders fields. We read the JSON files as a stream, one file per trigger from the feeders output directory. Convert timestamp strings to real timestamps and add a 1-minute watermark to handle late data. We group by 10-second tumbling windows and device, computing average temperature and humidity. Finally, we write the results to the console in update mode, so you will see the latest window aggregates as they arrive. Use Ctrl+C to stop this streaming job gracefully, ensuring Spark shuts down cleanly. Don't forget to include your requirement.txt file with all the required dependencies. You may be like, what does Spark no demonize mean? By default, Spark startup script fork the master, worker, or history server into the background as a daemon, setting Spark no demonize to true. Tell Spark to run in the foreground, no backgrounding. Why run in foreground? Running in the foreground gives you real-time logs directly in your terminal, which is great for Docker containers. So the container stays alive as long as Spark is running, and also for debugging. You immediately see startups errors or driver stack traces. And also for CI/CD pipeline, your build logs capture all Spark output without extra config. Simply export Spark no demonize to true before invoking any of Spark stats scripts. In Docker, you can add it into your .env or Docker Compose YAML, so every service inherits it. With .env.spark containing Spark no demonize set to true. When you run Docker Compose up, the master runs in the foreground, logging directly to Docker's std out. Now we created a Docker Compose file. Our Docker Compose file defines 3 services. The first is Spark Master, running our master node on port 4040 for the Spark UI, 1990 for the master UI, and 7077 for the RPC. Now, the second service, Spark History Server, for replaying past application logs on port 18080. And the last service, Spark Worker, for executing tasks, exposing port 8081. We also mount shared volumes for data apps and event logs. The Spark Master Service uses our custom Spark image built for the Docker file. We set entry point to launch the master role. A check pulls the master UI every 5 seconds to ensure it is up. Volumes include your IoT data directory, book data, Spark apps, and a named volume for Spark events. Similarly, Spark Worker uses entry points worker and links to the master. It shares the same data and logs volumes so workers can process the stream. The Spark History Server runs entry points history, reads the Spark events, and serves the history UI on the port 18080. We use an .env.spark file to pass environment variables like Spark no demonize to true. So Spark runs in the foreground. Ports map the container services back to your local machine, making UIs accessible in your browser. The first command builds all images, while this command tears down any existing setup, then brings everything up. This command boosts up 3 worker instances with scale Spark worker set to 3. Then this runs the stack in detached mode for background execution. Then we use make stop and make down to alt or destroy containers. And make submit executes Spark submit inside the master container, passing your app name under the apps directory. Now we are done with the implementation. Let us run our code. First, we are going to run the make run command to tear down any existing containers and run Docker Compose up to launch the full Spark cluster master, history server, and workers all in one go. You can see we have our Docker Compose running successfully. Next, let us submit our Spark job using the Spark submit. The -IT flags attach an interactive TTY so you can see streaming logs right in your terminal. This command starts the structured streaming application that reads those JSON files, aggregates them in 10 seconds windows, and prints results to the console. If you ever run into permission errors when writing or reading data, use this command to recursively grant read or write access of Spark data. This ensures both the feeder and Spark processes can freely read and write files. Lastly, we launch our Python feeder inside the DA Spark master container. This feeder simulates IoT sensor data, landing in opt-spark data IO stream directory. Visit localhost 1990 to see the master's dashboard cluster status and workers nodes as you can see on the screen. While your job runs, each Spark app exposes a UI on port 4040 by default. You can visit this port to view the jobs. For worker-specific metrics, check localhost 8081, just as shown on the screen. After jobs finish, review logs and metrics on port 18080. Here are some best practices. First up, reliability. To make your streaming jobs fault tolerant, always enable checkpointing so Spark can recover from failures. Pair that with write ahead logs to guarantee no data loss, and design your syncs like your database writes to be idempotent, avoiding duplicates on retries. This combination ensures your pipeline can restart cleanly and process exactly once. Next, performance tuning. The default Spark SQL shuffle partitions is often too high or too low. Tune it to match your cluster size and data volume. Equally important is proper partitioning of your input data. Quality small files, buckets by high cardinality keys, and avoid data skew. These steps minimize shuffle overhead and keep your tasks running in parallel efficiently. For scalability, set up auto-scaling executors if you are on a cloud or Kubernetes. Spark will add or remove executors based on load. Avoid monolithic group by operations on massive datasets by pre-aggregating or using incremental windows. And leverage caching for data reused across multiple stages, but uncatch promptly to free memory. Resource management is all about balance. Assign appropriate executor calls and memory. Too little and you starve jobs. Too much and you waste resources. In Yarn or Kubernetes, use namespaces and queues to isolate Spark workloads from other apps, ensuring predictable performance under contention. Don't forget data quality. Use watermarks to handle late arriving records. Enforce a strict schema on your JSON, Avro, or Packet input, and plan for schema evolution so you can add feeds without breaking your job. Security is non-negotiable. Enable SSL or TLS for both Kafka and Spark's internal RPC to encrypt data in flight via Kerberos or LDAP, and use RBAC on the Spark history server UI so only authorized users can see your job logs. Finally, capture data lineage and audit logs by integrating with your enterprise's governance tools. When things go wrong, here are quick pointers. Too large frame errors. Check your serialization format. Switch to Cryo or Avro with proper buffer size. Missing checkpoint. Verify HDFS or volume permissions and ensures your checkpoint path is consistent across restart. Need to peek at logs. Run docker logs -f spark master to stream master logs. Wanna test configs interactively? Launch the Spark shell to see how settings affect behavior before full deployment. In this video, we've seen how Spark Structured Streaming delivers low latencies exactly once, processing guarantees by leveraging micro batches, checkpointing, and write-ahead logs. By packaging Spark in Docker and orchestrating with Docker Compose, you achieve a reproducible multi-node cluster that is trivial to spin up or tear down. Finally, we stressed that proper tuning from Spark SQL shuffle partitions to executor sizing and rigorous monitoring via the Spark UI or external tools are essential for maintaining production stability and maximizing performance. Thank you for watching. Be sure you like, subscribe, and check the description for the source code URL.